Welcome to Rocket Science. Today we're going to be talking about global warming and the greenhouse effect. Now everybody's worried about it. They tell you about carbon footprint. They tell you about the Earth getting warmer than it was before and how the oceans are going to rise and your cities are going to flood and we're all going to die. So you probably want to look this up online to see what it's really all about. And you read these articles. They're really good articles. They have all kinds of data. They've got graphs, they've got charts. They're written by people who have studied this for 20 years. And when you read one, you say to yourself, wow, this is really good. This guy studied it all. He can tell me exactly how much the temperature of the Earth is going up. He can predict how much ice is going to melt and how all this water is going to change our life. Then you read another one. And this guy says, uh-oh, that other guy's all wrong. He miscalculated. He used the wrong data. And it's not really getting warmer, it's staying the same temperature, or maybe getting a little cooler. And the ice is just going through regular cycles anyway. And you say, well, okay, that guy was right and the first guy was wrong. Then you read the third one. And this guy says, oh man, that guy was wrong too. The Earth is going through natural cycles depending on the sun and the moon and the stars. And you don't have to worry about a thing. And you say to yourself, wow, I can't figure this out. I'm not smarter than a fifth grader, so I've got to depend on something. These guys are all arguing with each other, so what are we going to do? Well, today we're going to show you some ways to figure it out for yourself so that you can have a basic understanding of what global warming is all about, what the greenhouse effect is, and real things you can do to prove it to yourself. So let's start off with greenhouse effect. When I was a kid out here in Santa Clara Valley, they had these structures that looked like really long, skinny houses. They were all made out of glass. And inside, there was stuff. There was plants growing. And to show you what the greenhouse effect is about, I can draw a picture of what those look like. We had kind of horizon and these long glass houses like this. And there was a door in there. And up above, there were all kinds of vents that they could open up. And inside was green stuff growing, plants of all sorts. And they probably did this to keep control of the seeds that went inside, because I think they were growing flowers in there, and they wanted flowers of a certain type. So it was all green inside. And the greenhouse effect talks about the heat that gets built up inside of these. If you've ever gone and opened your car door on a hot day and you sit down in the seat and you get all burnt and it's really, really hot inside, well, that's kind of like the greenhouse effect. The sun is up here. And the sun gives all kinds of energy towards the Earth, huge amounts of energy. And the sunlight that's coming down, we're going to show you as tiny waves like that. They call that high-frequency light. That's pretend like this is the kind of light that we can see. It goes through the glass. The flowers absorb it. And they use photosynthesis to make the sugars and stuff that they need to stay alive. After that light goes into the greenhouse, it warms up everything that's in there. And the warmth looks to a scientist like long, lazy red waves like that. And in the theory of the greenhouse effect, these long, lazy waves don't make it out of the greenhouse. The glass is supposed to block them. So the light bangs into the glass and bounces off and keeps bouncing around inside and gets trapped. So they use this as an example to show what goes on Earth. So if instead of a greenhouse, you imagine the Earth there, it's got a thin layer of air all around it. The high-frequency light comes in, warms up the Earth, and as the Earth rotates, this warm land comes around to the dark side. And on the dark side at night, let's make it look dark. All this warm ground radiates the long waves out into the coldness of space, like that. Now, if there was no greenhouse effect, the Earth at night would cool off really fast. It would get much, much, much colder than it is now. It would get below zero, even in the places like the equator. And a lot of this high or long wavelength light gets trapped in the air. And it warms up the air at night. And this is what they call a greenhouse effect. The gases that get warm at night are trapping that heat and keeping it so that the Earth has a nice balance. Some of the gases that work good for this are carbon dioxide. That's the stuff that's in your breath when you breathe out. I-D-E. Another one is sulfur dioxide. If it's low enough. And then there's methane. That's called natural gas. And the biggest one of all is water vapor. That's just the invisible evaporated water that's in the air all around us. So those gases keep some of that heat in so that we don't get frozen. Now, that's the greenhouse effect that people have been talking about. It's not really like a greenhouse, because a greenhouse has barriers that trap the hot air inside. They don't let it escape. On the Earth, the hot air that's formed near the surface rises up and expands as it rises, and it cools off just from expansion, and it radiates its heat out into space. So there's convection currents. The air is actually moving in cycles up and down. There's conduction to various things that are there, like trees and buildings and everything. And there's the radiation out into space. So on Earth, we have convection, conduction, and radiation. Here in a greenhouse, you have the air trapped. So there's radiation is the main thing that keeps the greenhouse from getting really, really hot. So that's what the greenhouse effect is. It's not related at all to the ozone layer problem. At least that's what they tell us. And the thing that we're worried about is global warming. Now, global warming is when the heat going in on the sunny side is greater than the heat going out. And if you get too much heat going in and not enough going out, the Earth can gradually get warmer and warmer. There's a lot of heat stored in the middle. We'll talk about that later, but there's a bunch of it stored in the oceans and every place else. So we're going to talk today about the difference between the heat in, the heat out, and how these gases work to change the temperature of the Earth. We've just been talking about some gases that you may never have heard of before. Methane, sulfur dioxide, carbon dioxide, water vapor you've probably definitely heard of before. And these are different than ordinary oxygen that's in the air and nitrogen that's in the air because they behave differently when heat comes by. With oxygen and nitrogen, the heat pretty much just flies by and doesn't change what they're doing. Temperature is a measure of how fast atoms or molecules move. The faster they move, the more they bump into each other, that means a higher temperature. The slower they move, they have a lower temperature. At absolute zero, everybody stops. Now, things like water vapor, methane, and sulfur dioxide are made up of three pieces. For water, there's 2 hydrogens and 1 oxygen. Now we'll pretend like my body is the oxygen and these are the hydrogens hanging on. As I absorb heat, I can start moving faster, like running around like crazy, but I also do something else. The hydrogens start to move. Now, they can start going boing, 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 boing like this, and this energy is being trapped in the water molecule. So it's storing some energy, some of that heat energy. They might be offset, going one after the other. They might start to turn and twist. So there's all these energies that can be stored in water vapor. Carbon dioxide is similar. It's got a carbon in the middle instead of an oxygen. And it's got two oxygens on the outsides. And so that they can also vibrate. Sulfur dioxide is like that. Methane has got a carbon in the middle and 4 hydrogens. So imagine 4 balloons all doing whatever they want to do to absorb energy. One of the worst one comes out of your car exhaust pipe, nitrogen oxides. Those guys really do a good job of absorbing the heat and bouncing all over the place. So these are the gases that they call greenhouse gases. There's not very much of them in the atmosphere. Later we'll show you how much there is. But they absorb this heat and could possibly change the temperature of the Earth. If you were at rocket science and you want to burn something, there's lots of ways to do it. We have oxyacetylene torches, we got propane torches, candles, but this is one of the better ways to do it. This is a Fresnel lens taken from a projection screen TV. On the front of the TV there is some vertical lines on a piece of plastic, and sandwiched with that is this Fresnel lens. It has tiny circles, concentric circles, all cut into the plastic perfectly so that when the light goes through, it's focused at a single dot. A French guy, mathematician, invented this a long, long time ago. This one, luckily, has an area, a surface area of 1 square meter. And the sun, at the equator of the Earth, can put 1,000 watts on 1 square meter of stuff. Here in Santa Clara, it's more like 700 watts on a good day. Today is really overcast, so we have considerably less than that. But it focuses that dot down to about the size of a marble. So you get a huge magnification of the light. On good days, it gets over 2,400 degrees in the center of that dot. On a day like today, it's probably more like 1,400, 1,500 degrees. This is the sunlight from a magnifying lens. It's almost exactly 1 square meter of sunlight focused on the dot. As I rotate the frame, you can see the fire brick move under the dot. On a good day, the light is so bright and so hot it melts our fire brick. Here we're going to put some things in the bright spot so you can see what they do. This is just a piece of plastic, green plastic. You can see it expand on the surface as it gets hot. It starts to melt. Looks kind of like a turtle shape. And once it gets black, it absorbs more of the heat. Now you can see a flame is consuming the plastic. Now we're going to try a penny. Penny's got some water on it. There's Abe sitting in the hot sun getting a suntan. And hopefully you can see that he's changing color a little bit. Now his face is starting to melt. Poor Abe. And there goes Abe. So sad. And the zinc is all melted out from under him. There, the penny just got cooled off. If we try a marshmallow, of course, should just burst into flame. Now, the Earth reflects light from its surface, mostly because of the clouds. At any one time, the clouds cover about 40% of the Earth. If we put a marshmallow on here, it's kind of like our clouds, the light is diffused, it's spread out, and it's reflected off because of its super white color. So even though this has a much lower melting point, where the dot is doesn't burn until the backside, which was touching the brick, was so hot it caught on fire. We just let our marshmallows sit there. See, now if we had some chocolate, we could make s'mores. The sugar in the marshmallow, the temperature is so high that sugar is made out of carbons and hydrogens. It burns off the hydrogens and leaves carbon ash. See it there? It's hollow. All its guts got gushed out over here. Let's see that. We'll let it drift off. Now what if we put a piece of 2x4 on there, just to show what it's like. You see how quickly the 2x4 ignites. And this immediately evaporates all the water in the wood. And the cellulose that wood is made out of is also carbon and hydrogen. Burns off the hydrogen to make water vapor. And the carbon guys burn off and become carbon dioxide. Those are the only two products. If something burns completely, like wood or plastic, they only make carbon dioxide, water, and heat and light. So now this thing is toasted. When we talk about global warming, we have to collect data and look at the data to see if it really is getting warmer. In the 60s, they were talking about nuclear winter. They were worried that the Earth was getting too cold. In 1962, there was snow here in Santa Clara Valley. You could make a snowman in your front yard. It was one of those very cold years. And during those particular years, they were worried that the entire Earth was going to get too cold and we were going to have a big problem. And then things started to heat up more, and now they're more worried about global warming. So how much is it going to get warmer, and how much has it already gotten warmer? In order to figure this out, you need data over a long period of time to see what's going on. And it would have been nice if 400 years ago we had thermometers like we do today, and they were all spread out over the Earth, and there was people collecting all this data, and that we could now analyze and see, yeah, there's a definite trend. These thermometers are all identical. The people that are reading them are doing a good job, and we know what's really happening. Unfortunately, we don't have that kind of data. We have thermometers that have changed. We have people that have changed. The positions of them have changed. We have to just kind of look at what's there and decide for ourselves. And even with today's data, on the movie An Inconvenient Truth, Al Gore drew a graph that went along and kind of gradually rose and then went ka-zoom, way up into the air. And everybody said, oh no, this is terrible. Well, then later, the guys at NASA, because of some other pressures, took another look at the data and they said, oops, there was a small error in that data. It doesn't go ka-chunk as high as it did before. It's less of a slope than before. And this is with, modern data, modern instruments. They made a mistake and corrected what they did. Now, we want to give you some idea of the difficulty of this so that you can understand the magnitude of the change and how hard it is to actually measure the temperature of something. Now, suppose you wanted to measure something pretty easy, like the temperature inside your house. There's many rooms in your house, and there's different kinds of thermometers you can use, and you can wander from place to place and set the thermometer there for a while and measure the temperature. And if you record that temperature, then you'd have some data about your house. But you might say, well, if I measure the temperature early in the morning on one day and then later in the afternoon on another day, that won't be a good comparison because it gets warmer during the day. So you're being smart. You say, okay, I'm going to measure the temperature exactly at noon every day. And when it gets to be daylight savings time, I'll compensate for that. So every day at noon, you go and start making your measurements and you write them down on a piece of paper. Then you say to yourself, well, the seasons change too, so I'm going to have to do this at least for a year to get back to where I was before. So if I started in June, on June 1st, say, of one year, I have to wait till June 1st the next before I can make any conclusions at all just because of the changing of seasons. Well, that's kind of a problem, but imagine your thermometers. What if you decided to put individual thermometers throughout your house? Do they all work the same? Do they all read the same? These kinds of thermometers have a bulb down at the bottom with some alcohol in it that's got some red food coloring and a really thin tube, and it's sealed off at the top. They're pretty well made. And just sitting here on the table, these were all reading about 25 degrees Celsius. And it was within about 0.2 of a degree. And you just look at each one. If you got a magnifying glass out, you could have looked really carefully because the degree marks are in 1 degree increments. So if it's 24.5 or 25.5, you can't really tell unless you kind of fake it. You say, oh, well, it's closer to 24 than 25. So a thermometer like this, if you got good eyes and maybe a magnifying glass, you could estimate the temperature within 0.2 of a degree. And between thermometers, there's also an error of about 0.5 degree from one to the other because they can't make them perfectly. If you compare different brands of thermometers, this guy here was saying that the temperature of the table is 26 degrees. So it's off 1 whole degree more than the other guys. And this is a problem, a real problem that the scientists face. Were the thermometers the same everywhere on the planet? Did the cycles of the planet change things? You know, they've got to go year after year after year and hope that nothing else changes because they're looking for temperature changes on the order of 1/10 of a degree centigrade or Celsius. Now, there are other kinds of thermometers as well. A thermometer like this doesn't have alcohol in a tube. It's got a trigger on it, and it's got a screen. If I point it at myself and turn it on, it reads some temperature. And it says I'm 31.0 degrees centigrade or Celsius. So what's it doing? It's got an eye. And the eye actually looks at the light coming off of me. The type of light that it looks at are these long waves that we talked about, those long red waves, the heat waves, infrared energy, and it's calibrated so that it knows what infrared energy is what temperature. So it gets an idea of the temperature of me based on my light. Doesn't even have to touch me. There's cheaper versions of that you can get. They also have a little eye in the front, and you can point them at yourself. And this one says, I'm 31.3. Let's see what this guy says. Boink. It says I'm 31.1. And this guy says I'm 31.2. So these guys also have problems. If you imagine a satellite flying over the Earth, a satellite has different kinds of eyes that are looking at different frequencies of heat that's coming off. And it scans over the planet and tries to check out the temperature. It can't look at really small points. The satellites are so far up that they're looking at a broader area. And there's problems with that as well. If there's dust in the atmosphere, if there's clouds in the way, if the temperature of the air is different than the temperature of the land, and there's all these factors that will change their readings. So it's cool to have satellites up there. They paint a huge picture of the entire planet so we can stand back and look and say, these are the big trends. And at least with a satellite, the temperature measuring devices are the same ones, but they aren't there from history. We don't have satellites that go back past by about 1970, and those were different than the ones we have today. So we can look at the last few years with satellites, but there's no way we can determine what was going on 100 years ago with the satellites. Now, you can see that these thermometers didn't all agree with each other. And you can do a great experiment with your kids around your house. Go buy a bunch of cheap thermometers, put them in the different rooms, and let them take readings. Have one child take readings whenever he feels like and actually write them down. And have another one take readings whenever they feel like and have them write them down. And then after a week or until they have one page filled with numbers, have them compare the two. Pretend like this is exalted scientist number 1 and this is exalted scientist number 2. And they have to fight for their readings. And it's highly unlikely that they'll agree because they'll take them at different times of day. Now, the same thing goes on with scientists. One scientist has weather stations in this part of the earth. Another one has weather stations in that part of the earth. Some of them are using satellites. Some of them are not using satellites. They measure at different times of the day, different times of the season. Everything is changing. And they're arguing over their data. They can't even get 2 thermometers to read exactly the same at any one spot. So when you're talking about global warming, you need to kind of take it with a grain of salt. How much accuracy do they have in their readings? And how big is the change they're talking about? If their readings are accurate to 1 degree and no better, and they say, oh, well, the Earth is getting warmer by 1/10 of a degree, sorry, you can't say that. You don't have enough accuracy to conclude a 1/10 of a degree change. And just doing it at home with your own stuff, your children will then understand what's going on. Let's suppose that Jack and Jill moved to the moon. We need a little bit of moon here. There's all kinds of hills on the moon. And they've built for themselves a huge dome to protect themselves and to trap some atmosphere so that they can breathe. Kind of blot that out. And on top of their dome, they put a solar panel so that they'll have some electricity. And off in the distance, we've got some sun up there. To give them some power. And Jack and Jill need water to survive. There's just no way you're going to do it without water. Luckily for them, their dome is close to the poles, and they've dug a well. And they now have a bucket in their well on a rope. And they can lower their bucket, but they don't get water. It's a special bucket. It's got eyes, and it's got arms, and it can dig in the ground, and they bring up dirt, and the dirt is all filled with crystals of ice, frozen water. And then Jack and Jill have to melt the water out of the ice, or out of the dirt, and create for themselves a pond. So they've got enough water there to survive. And with the electricity from their solar cells, they can put electricity through water and turn it into hydrogen gas and oxygen, which is a very good thing because they can breathe the oxygen. And we'll put Jack and Jill in here. The oxygen part is great because without it, they die. The hydrogen can be used as fuel for their rocket ship when they want to go back. There's a door there. Jill's hair is infinitely long. There. So they store all the extra hydrogen in this big tank they brought along. We're going to abbreviate hydrogen as H2. Do not touch. Like that. So Jack and Jill now have oxygen to breathe. They've got water to drink. They've got hydrogen for fuel if they need it. And they've stored their spaceship inside. Their spaceship happens to be a rocket-powered caterpillar. There. And they still need other things. They need a garden because they like to eat bread. They like to have trees growing so they can have fruit. And we'll put a tree in there. They want all of the stuff that they had on Earth growing here in their moon colony. And Jack and Jill have brought along with them their friends. Their friends are called kickme's. And the kickme's are very sad little guys. They look kind of like a bowling pin. Boink, boink. And they're always unhappy unless you kick them. That's why they have that target on their stomach. The harder you kick them and the more they bounce, the happier they are. They're kind of like little rubber people. They're indestructible. You could throw a kick-me into a jet engine and he'd come out the other end like smoke. And the kick-me would be laughing and giggling and the smoke would reconstitute itself and it'd be a kick-me again. So they brought a bunch of those along with them to the moon as companions. There. And they can kick them real hard and bounce them around inside of their dome. Sometimes it gets too hot in their dome. So they have something like clouds that they suspend from the ceiling that are reflective. They can bounce the extra sunlight off and they can rearrange these clouds to change their temperature. Well, other people found out about this. Jack and Jill with a successful colony on the moon. This is great. What a neat thing to have happen. And one of the people that found out about this was none other than the evil Mr. Fred. And being that he's evil, he decided to put his own moon colony up right next to theirs. So evil Mr. Fred built himself a castle right near Jack and Jill. And when Jack and Jill saw this, they didn't know what to think. Every time evil Mr. Fred comes around, things go from bad to worse. And here he was, building a castle. And evil Mr. Fred didn't build a nice dome like Jack and Jill did. He went and bought himself from the Acme store of everything, the world's largest garbage bag. And he built his castle inside of this big old garbage bag. And he sealed it all up so that he would have air inside. And of course, evil Mr. Fred doesn't do any of the work himself. He has his friends, the minions. The minions aren't too bright, but they always try to please. They have no arms. They have to do all their work with their mustaches. And their favorite tool is a baseball bat. Whenever you need something broken, you call a minion. And evil Mr. Fred built his castle there. He said, "Ha! Doesn't take a genius to do this. I'm all set. Look at all the work they went to, and I did it in just a couple of days." And then he started having problems breathing, and it was getting too cold in there on some times, and way too hot other times. And evil Mr. Fred said, "Uh-oh, this is bad. We've got to figure out how to solve this." So he put shovels on the end of the minions' baseball bats. He said, "Minions, your job is clear. You've got to dig a tunnel over to Jack and Jill's area, and we're going to take whatever we want." And the minions said, "Yay, boss, this is fun. We'll do this." So the minions started digging holes. And they dug underground. And the first thing they did was dig a hole near the garden, hidden in the bushes. And once they broke through, they were able to take air out of Jack and Jill's moon colony. And they said, "Ah, finally, fresh air. This is much better than it was before." Then they dug another tunnel over to the pond right underneath. And they were able to steal some of Jack and Jill's water from their pond. And now they had water to drink. And they went and snuck in there late at night and put some wires up to Jack and Jill's electric supply from their photocells. After just a couple of days, evil Mr. Fred had everything he wanted: food, water, clothing, fresh air, everything he took from Jack and Jill. Well, it didn't take long before Jack and Jill realized that evil Mr. Fred was stealing their stuff. And they didn't know what to do. If you were Jack and Jill, what would you do to stop evil Mr. Fred and to fix all the things that he's messed up? Because when evil Mr. Fred takes stuff, he doesn't just take a little, he takes a lot. The Earth gets its heat from two places. The major spot is the sun. In 24 hours, the sun shining on the Earth produces more energy than mankind does in about 30 years. So that's a huge input of energy. That happens during the daytime, of course. As the Earth rotates, that heat is radiated out into space. And the space has to draw out the same amount that the sun put in minus whatever's stored. It gets stored in the oceans mostly. And every time the Earth rotates, it gets this enormous input, goes to the dark side, radiates out into space, and it keeps going and going and going. If there's a gradual increase in temperature, that means that something is out of balance. Either the space isn't sucking it out fast enough, or the sun is putting it in too fast, or whatever's being stored is letting it go. And about, 1/4 of what the sun gives us gets absorbed in the atmosphere by various gases. We want to show you which gases are in the atmosphere so you just have an idea of what's going on. Now, one of the gases, the majority, is nitrogen. And we're going to represent nitrogen with this box of colorful cereal. The atmosphere is about, I think 78% nitrogen. And we measured out enough cereal here. So this looks like about 78% of what we're going to end up with. There's 7,800 of those guys in this bucket. The next one we have is oxygen. Oxygen is represented by these little brown guys here. And there's about 2,000 of those. So far, our atmosphere is about 78% nitrogen, about 20% oxygen. Next we have argon. Argon is represented by these fuzzballs. There's about 100 of those fuzzballs in there. And next we have, carbon dioxide. Carbon dioxide is represented by these 4 black fuzzballs. Now, of the carbon dioxide, some of it is being produced by man. According to the majority of the estimates that you'll find online, about 1% of all the carbon dioxide that's in our atmosphere was put there by man. So these 4 BBs represent what mankind has put into the atmosphere in the way of carbon dioxide. Now, some people argue that there's got to be a lot more carbon dioxide somewhere, because in the daily cycles of warm and cold, plants waking up and going to sleep, the carbon dioxide levels go up and down and up and down. Now, they're highest in the morning when the plants are just waking up. So when the plants get up, they're hungry, the sun shines on their leaves, and they start sucking in carbon dioxide. And as the plants use more and more during the day, the level goes down and down and down and down. And then when the plants go to sleep at night, the carbon dioxide levels rise again. And so each day there's this cycle. If carbon dioxide is driving the temperatures on the Earth, we would expect that the temperature would go down as the carbon dioxide levels go down, and the temperatures would go up as the carbon dioxide levels go up. But in fact, it's the opposite. During the day, as the carbon dioxide is being used up by the plants, it gets hotter. And at night, of course, it gets cooler. To show you how all this stacks up, we're going to put our nitrogen in this bucket. There it goes. There we have our 78% nitrogen. It's not called the greenhouse gas. It doesn't absorb nearly as much energy per nitrogen thing as the carbon dioxide does, but there's a lot of it. And we'll do the oxygen. There goes the oxygen. And oxygen tastes good too. Here's argon. Most people have never heard of argon. Argon they put inside of light bulbs. They use it in welding. It's a type of gas that doesn't react with anything, and it's just there. Spread that around. And here comes our carbon dioxide. Now, there's one we haven't mentioned. There's one that is a much more powerful greenhouse gas than carbon dioxide, and that is water vapor, represented by our marshmallows. Because the water vapor goes up and forms clouds. And there's the water vapor. Water vapor is mostly lower in the atmosphere, so we use a lot of it to represent what's in the atmosphere where everything takes place. The greenhouse effect works mostly at night. That's when the sun has already warmed up the ground. The infrared radiation from the ground goes up through the atmosphere and is absorbed by the various gases. When I first found out about this, I thought, wow, carbon dioxide can do all of that, and it's such a tiny portion of our atmosphere, it must be just an incredibly good gas at absorbing infrared. So I thought, wow, this will make a great experiment. I'll take a bag, fill it with carbon dioxide, and dangle it in front of some source of infrared light, and see the temperature just zoom up. But I would need a control to do that. So I could have another bag full of air. I might have another bag full of breath from a person, and another bag with no carbon dioxide at all in it. And since water vapor actually absorbs more of the heat, I should have one with no water vapor in it. So I've collected a group of bags that you see behind me that have various amounts of the gases in them. And we're just going to let them absorb some heat from this warehouse that we're in. It's like a nighttime scene. We have very little lights going on. So we're getting a lot of this very low level radiation going into these bags. Now, you can do this at home. They're just ordinary clear garbage bags that we puffed up various ways. If you want to, you could hang a thermometer right inside each bag and then just read it every once in a while and get a comparison of what goes on with these various gases. To make it a little bit easier, we're going to use an infrared thermometer that we showed you earlier, and we can just point it at each bag to see what the temperature is. So here we have one bag, 100% CO2. There's a couple of ways to make this, but we just squeezed all the air out of the bag, put in a couple of chunks of dry ice, and waited for the dry ice to fill up the bag. Then we put a rubber band around the top. And temperature of this bag is 28.2, 27.8, 27.7, 27.6, 27.7. Just to give you an idea, it's around high 27s to about 28 degrees. Now let's take the next bag. If you blow up a bag with your breath is about 12% carbon dioxide. That's 300 times more than what is in the atmosphere. So let's take a look at this guy. He's 28.0, 27.9, 28.0, 27.9. He has some water vapor in there too, because when you breathe out, you have a bunch of water vapor in your breath. So he's pretty close to 27.9 to 28.2. Now, we have a bag next to it. It's got some white powder in the bottom. The white powder is calcium chloride. It absorbs moisture from the air. So by shaking the white powder around and letting it dangle here for a while, we've eliminated any water vapor that's in this bag. So it's ordinary air, no extra carbon dioxide, it just has no water vapor. And its temperature is 28.1, 28.0, 28.1, 28.0, 28.2. Okay. Now let's move over to our poor sad bag over here. Had a little bit of a leak in it, and this one has no carbon dioxide at all. We put lime water in there, and lime water absorbs carbon dioxide. To give you an idea, here's a cup with some lime water in it. I'm going to put this black card behind it, and when I blow bubbles in it, the carbon dioxide in my breath should make a change in the water. And I can see that the water turned all milky. We formed calcium carbonate in the water with carbon dioxide from my breath. You can make lime water at home. If you go to the garden supply, you buy hydrated lime. It's a white powder. Put it in water, let it settle overnight, and just take off the clear water off the top and let your kids blow bubbles in it and see how it turns. You know, they can just blow bubbles till the cows come home, and it'll get whiter and whiter as they go. In this bag, the lime water has absorbed all the carbon dioxide. It puts a little bit of extra water vapor into the air. So let's see what temperature it is, plus the liquid water too. It's 27.5, 27.6, 27.7, 27.7, 27.6. Okay. So the highest we had so far was about a 28.1. Now let's just take plain old air. Just wave the bag around, let it get filled with air. It's 27.9, 27.2, 27.3, 27.5, 27.4. It seems to be settling down right around 27.5. So you can see that the temperatures aren't that different. About 27 over here. The carbon dioxide again was about 27.5 or 6. And that's 100% carbon dioxide. So carbon dioxide isn't a magic gas that absorbs huge amount of energy and gets really hot. It's one that when it does absorb some infrared energy, it trades it off to other gases that are in the air. But it's not really powerful. So when you're thinking about your carbon footprint and how much carbon dioxide you're producing, think about how much is actually in the air. You remember when we poured all these cereals into this big old tub? The carbon dioxide was equal to 4 of these black fuzzy balls. The rest of it is other gases. There was a couple of hundred of the water vapors in there, which are far more powerful than carbon dioxide is at absorbing heat in the atmosphere. Also recall that the amount of carbon dioxide created by people is equal to 4 BBs, these little tiny balls that you put in there. So even if mankind stopped producing carbon dioxide altogether, the effect would be very, very small. So these kinds of things are up to debate. Scientists are just having a great time saying, I'm right, you're wrong, or you're right, I'm wrong. And to collect data and actually know what's going on, we're not there yet. But if you would like to join us and do some experiments and share your information with us, we'd love to collect it. If you can get some clear plastic bags and blow one up with your breath, 300 times the amount of carbon dioxide that there is in the atmosphere. Hang it outside somewhere at night after a warm day and monitor its temperature. If you like, dangle a thermometer inside. If you want to get one of the cheap infrared thermometers, we can tell you on our website how to get one of those. And dangle one with your breath in it. Maybe if you want to, you can dangle one with 100% carbon dioxide in it, just for fun. You could dangle one out there with some ordinary air in it, whatever you feel like, and tell us what you find out. It's going to be different for different parts of the country. If you live in a heavily forested area, you may get different results than somebody living in a desert area. If you live in a place where it's extremely cold, it should be different than some place where it's extremely hot. We don't know what's going to happen, but this will be important information for us to help to decide what we should do if the Earth starts getting warmer and warmer. Now, as far as you're concerned, you should just know that there's not a heck of a lot of carbon dioxide out there. All the plants, the algae, everything that's green on Earth uses this stuff. And in our Earth, they have something called the carbon cycle. Where does the carbon come from and where does it go to? So I'm going to show you with a quick picture where the carbon comes from and where it goes during its life. Where does carbon come from and where does it go? Some people say all the dinosaurs died, the forests all died, they went into the dirt, got covered up, pushed way down, and that gave us the carbon that we now have. But that begs the question of where did they get their carbon? So somebody came up with some pretty good explanations. They said that the Earth has land on it, and the land comes in pieces. They call them tectonic plates. So we'll draw one here. And we'll say that this one is just kind of sitting there. And this other guy, he's not happy where he is. He's moving that direction. And he's ramming into this guy and kind of going under him, like that. Where they hit together, they usually form mountain ranges. So we'll put some mountains in here, like that. And beneath both of these plates, there's a whole bunch of magma, hot lava. And it doesn't just sit there, it moves around as well. And this plate is being driven downwards by this guy. Now, let's suppose that this mountain here happens to have some holes in it, and it becomes something that is fun. It becomes a volcano. And let's put an ocean out here, whoosh, like that. Now, when a volcano erupts, it puts all kinds of smoke and ash and gases into the atmosphere. One of the more common gases in a volcano is carbon dioxide. We abbreviate that CO2. And the carbon dioxide guys are all floating around in the air. But one thing that carbon dioxide really likes is water. When one of these guys happens to hit the water, it doesn't bounce off. The water grabs it, and it goes down into the water. it dissolves right in the water. So now there's a bunch of it down in the water. And it doesn't just stay there either. There's critters in the water. And some of our critters grab that carbon dioxide and they use them to make their shells. So if you look at any shellfish like clams or anything else that's got shells down there, they grab the carbon dioxide, take off the oxygen part, keep the carbon part, and, well, they don't take off all the oxygen, they only take off one, and they combine it with some calcium. They call it calcium carbonate. And all the seashells have calcium carbonate trapped in themselves, and they live and they die and they pile up on the bottom of the ocean. Now, over thousands of years, maybe millions of years, the bottom of the ocean gets pushed downwards, comes in contact with the magma, and melts. Well, all that carbon that was trapped down there in those seashells melts along with it and becomes part of the magma. And the magma comes up through a volcano. It could come up in the atmosphere like this and spew out and repeat the whole cycle. Or sometimes we have vents under the oceans. And those guys also spit out carbon dioxide and it goes directly into the water. We don't know how many of those guys there are. Probably a lot of them. And the ocean absorbs this carbon dioxide. Some people say that carbon dioxide absorbed in the ocean isn't a factor in global warming. Other people say it is. And one of the better reports said that deep, deep, deep down in the ocean, there's a lot of carbon dioxide. And they have an explanation that seems pretty common sense that we'll show you in just a second. Here's a bottle of ordinary water, and currently there's air above it, oxygen, nitrogen, and all the other gases. I'm going to squeeze it until there's nothing pretty much except water in there. And we'll put this cap on. Now we have a squished bottle, a little tiny bit of air is in it, with a cap. We have a tank here that has carbon dioxide in it. When I turn this lever, the carbon dioxide will come through this hose and into the bottle. And there it goes. I'm going to turn the bottle upside down so you can see the carbon dioxide going in. And you notice it goes in and then it stops. I want more to go in though, and I'm impatient. So, being like a kid, I could either hit it and a little bit more goes in, or I could shake it. And now you can see more bubbles after I shook it. This is kind of the opposite of the old thing where you shake your soda bottle and spray soda all over your brother. In this case, we have to shake it to get carbon dioxide to go into the water. Every time I shake it, more goes in. This is how they make soda water. So when you buy a bottle of soda water, they don't actually have people standing there shaking it though. They have a better way to make it go in. Because when they're making soda water, they don't use plastic bottles, they use steel tanks. And if you increase the pressure, currently we're at about 30 pounds per square inch. Let's see what happens when I increase the pressure. See more bubbles? Bubble, 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 bubble. That's about 35. Let's go up to 40. There's about 40 psi. You can see that the more pressure of carbon dioxide, the more you can fit in there. At the bottom of the ocean, suppose the ocean is 10,000 feet deep, and there's a volcanic vent down there. the pressure of the carbon dioxide in order to escape from the volcano has to be greater than the pressure of the water. So down there, there's 5,000 pounds per square inch of carbon dioxide forced into the water. That's a lot of carbon dioxide. And it's very, very cold down there. So it turns out that cold water can absorb more carbon dioxide than hot water. This is just room temperature water. So if you wanted to make fizzy water at home, you would probably start off with very cold water and do the shaky, shaky thing and get it to come into your bottle. So we're going to just shake it a couple of times until it looks like it's just about done. We do this with kids in our science classes, and they just keep going and going and going. Because they like to shake it a lot, of course. Roop, roop, roop. Now, we're going to turn the carbon dioxide off. Let it drain back into the bottle. Release the pressure. The water doesn't look any different than before. It looks clear. We'll take lid off. Did you see the bubbles rise out of that? And we have created soda water. Now, how much is in there? It's hard to say. We could do a test. Here we have a balloon with 3 Mentos inside, and we have our bottle of carbonated water. We're going to put the balloon on the bottle and then let the Mentos go free. Okay, on there. Let them fall into the water and shake it up a little bit. Now we're releasing it. Boink. Now we can see that we have this amount of carbon dioxide plus this much was trapped in the water just here at room temperature with about 40 psi of carbon dioxide. And remember that down beneath the ocean, the water is colder, which will allow it to store more carbon dioxide. And the pressure there could be 5,000 pounds per square inch. So it should store a whole lot more. Let's turn it upside down and see what happens. Boink, 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 boink. Boink, 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 boink. So it looks like the water didn't store quite as much carbon dioxide as its own volume. And in some of the bottles, we'll see that the carbon dioxide stored is a whole lot more. But that'll be our next experiment. Skewered on a bent paper clip, dangling over a pool of death. When they fall in, the Coca-Cola is going to dissolve off their covering and create a rush of carbon dioxide gas. That would propel it way up into the sky. That was a room temperature bottle of soda. And after it settles down, we can see that the liquid is about there. So it's driven off about that much of the actual liquid. I'll leave that for comparison. Now we have a bottle of the same soda that is cold. According to the thermometer, 32 degrees Fahrenheit, about 0 degrees Celsius. Here we go. Now, what do you think? Will cold Mentos and cold soda go higher or lower than room temperature? We'll find out. There it is. The cold stuff didn't go as high. So sad. We should cut off the label so you can see how much is left. So this one only spit out about that much. This one has been sitting in warm water, so it's at 43 degrees Celsius. That's 109 degrees Fahrenheit. If you listen, you'll hear some carbon dioxide escape. There we go. 5, 4, 3, 2, 1. And there we have it, 109 degrees. Compare that to room temperature. Looks like the room temperature guy was a little bit more efficient. It's spit out a little bit more. And of course the cold stuff was quite a bit less. Now there's ingredients in the Coca-Cola that help it trap carbon dioxide gas. That's what's driving it out. We're going to compare this to a room temperature bottle of plain water. It has no other ingredients other than the carbon dioxide gas. Already you can see carbon dioxide wants to get out of there. 5, 4, 3, 2, 1. That's all you get. You can see that the Mentos there are sitting in the bottom, fizzing away, but you don't get an explosive burst of CO2 out of the bottle. First, drill some holes in the little critters. These are about 1/8-inch holes. And I use a high-speed drill and just do a couple hundred at a time. Then you straighten out a paper clip and thread them all onto the paper clip. You can put as many as you like. I've been using 5, but other people have had better results with about 7. And you have a cap. You drill about a 1/4-inch hole in the cap. Slide that over the little critters. And to keep them all together until you're ready to fire, you put on a paper clip, screw it onto your bottle. When you're ready to go, you pull the paper clip, the Mentos slide through and down into the drink. That's all there is to it. When we left them, Jack and Jill had established a moon colony. They did a pretty good job. They figured out how to get some ice out of the ground, how to melt it to form water, how to get some electricity from their solar panels and turn the water into hydrogen and oxygen. They stored all the hydrogen in this tank. Of course, the oxygen they could breathe. And the more they breathed, the more carbon dioxide they produced. And the carbon dioxide was used by the plants in their garden to grow, so they had food. And they also had all the kickmeas there, and they could kick the kickmeas all over the place, and the kickmeas would laugh and giggle as they got bounced all around inside of the place. And they also would produce carbon dioxide. The extra hydrogen they were planning on using in their rocket-powered caterpillar when they decided to return to Earth. Now, evil Mr. Fred had come along and established himself his own moon colony close to theirs. And of course, he had tunneled into their moon colony and was stealing air, he was stealing electricity, he was stealing water. And every time he would take some, Jack and Jill would have to compensate by doing some extra stuff. Like when he stole some water, they had to go and dig a bunch more ice up and get enough energy to melt that ice to make water. When he was stealing their air, Jack and Jill had to run more electricity through the water to produce more oxygen. And of course, he ran some wires up there to steal their electricity too. So Jack and Jill were always constantly struggling, trying to balancing everything out so that they could compensate for what evil Mr. Fred was doing. Well, one day, evil Mr. Fred noticed the tank over in the corner. Said, "Do not touch." He said, "Well, whatever that is, I want it. They like it, I want it too." So he had his minions tunnel further until they were right under that tank. And he says, "Okay, minions, Whatever it is, go get some. And the minions dug their way over there and they got to the bottom of the tank. And usually they don't do things very well. But this time they managed to drill a hole in there and put a fitting on it and run the gas from the tank down their tunnels and up to evil Mr. Fred's place. And evil Mr. Fred said, "Well, what is this?" The minion said, "We don't know, boss. We just did what you said." And evil Mr. Fred said, "Cool." And he turned on the handle on the end of the faucet there, and out came all this hydrogen gas. It smelled pretty bad. And evil Mr. Fred said, "Well, what on earth is this? It must be good because they have it." And he kept shooting out more and more of it, and he didn't know what to do. And he thought, well, I need a cigar so I can get my brain working. So he pulled a cigar out of his pocket and put that cigar in his mouth. He says, "I'll just smoke this cigar while I'm thinking." And he lit a match. Well, it turned out that that gas was hydrogen gas. And evil Mr. Fred had put just the right amount in his big garbage bag and in his castle. There was this enormous explosion. Flames shot up. And evil Mr. Fred launched himself, his minions, and his castle clear out into the outer reaches of space. And everybody lived happily ever after, except evil Mr. Fred.